Okay, hello everyone. In our last class, we have been discussed in general about cardinal points and cardinal planes of an optical system. For any optical system, we can found 6 cardinal points that are first, second focal points, first, second principal points, first, second nodal points. In detail, we have been discussed in our last class. Okay. In this class, we are going to discuss location of cardinal points and cardinal planes of an optical system. Before we are going to discuss today's topic, let us just recall what we have been discussed in our previous class. In that class, we have been discussed about system of matrix, which is represented as S subscript small m of an optical system. Okay, here you can see this yi alpha I represents about object or input or initial information. This one in the figure, this one yi. This one yi alpha I in matrix form. This is in your 2 cross 1 matrix form. Yo alpha O represents about image or output or final information in matrix form. This is also a 2 cross 1 matrix. This is your Yo alpha O in output plane, yi alpha I in input plane. Here you can see 5 matrices are multiplied, formed a matrix which is a 2 cross 2 matrix and called as system of matrix. So here SM, here for this case SM, that is your system of matrix, is nothing but your multiplication of these 5 matrices: translation, refraction, again translation, refraction, and another translation. In detail we have been discussed. So this equation also can be written as like this. Here Yo alpha O is equal to, instead of multiplication of these 5 matrices, we can write simply SM yi alpha I. Okay, so here SM, system of matrix, is act as an operator, because when system of matrix SM is operated on initial information, we can get final information or information about image. If I'm going to consider system of matrix of optical system considering thick lens, this one, see here this SM represents system of matrix of whole system. But if we are going to consider system of matrix of optical system, that is your thick lens, this one, the system of matrix will be multiplication of these 3 matrices. How that we discussed in that class itself. So here system of matrix act as an operator. In general, it is represented as A, B, C, D, 4 elements in matrix form, because here if I'm going to multiply 5 matrices, also we can get 2 cross 2 matrix. Final matrix will be a 2 cross 2 matrix, because here each and every matrix is a 2 cross 2 matrix. This one T M3 also 2 cross 2, R M2 also 2 cross 2. So each and every matrix is a 2 cross 2 matrix. So after multiplication of these 5 matrices, we can get final matrix also will be a 2 cross 2 matrix. Similarly here, if I'm going to multiply these 3 matrices, also we can get this SM for thick lens also a 2 cross 2 matrix that we have been discussed in our last class. So simply you just remember one thing, that if we have information about object and I'm going to operate system of matrix on this object information, we can found the information about output or image. In general, it is represented as like this. So this is the concept that you have to remember. It is very important, because by using this concept, we are going to evaluate location of cardinal points of any optical system. Okay, in that class also we discussed any 2 cross 2 matrix could not be accepted as system of matrix if and only if its determinant will be 1. If determinant will be 1, then it will be accepted as a system of matrix. So I suggest you just remember this concept, that when a system of matrix will be operated on object information, we can found information about image. Okay, so let us move to our today's topic. Here I written the heading that location of cardinal points and cardinal planes of an optical system. The figure represents in general a optical system which is present in between input plane and output plane. Here I am going to show you. This is the input, this is the optical system. This is a optical system which is enclosed in between these two planes. This is your input plane and this is your output plane. Okay, and this optical system may be a thick lens, may be a combination of two convex lens, may be combination of one convex one concave lens, or maybe combination of two concave lens, whatever may be. So in general, a optical system enclosed in between input plane, which is represented by I1 I2, and output plane O1 O2. Okay, and here x dash is the principal axis of the optical system. About principal axis already we have been discussed. Principal axis is the axis of symmetry, okay, which divides equally upper and lower half of an optical system. And if a ray will propagate along the principal axis like this, along the principal axis, then it will move without any deviation. It will pass through the optical system, but it will not deviate anywhere. So from input plane to output plane, the ray will move undeviatedly if it will be passed through or propagate along the principal axis. Here mu I and mu O represents the refractive indices of left or input and right or output side of the optical system. Here this side is your left side, having refractive index is your mu I. This side is the right side of the optical system, having the refractive index is your mu O. Okay, I for input, O for output. Okay, mu is the refractive index of optical system. This is the optical system having refractive index is your mu. Here F1 F2 P1 P2, let F1 F2 P1 P2 N1 N2 are the first and second focal, principal and nodal points respectively. Here F1 F2 P1 P2 N1 N2, 6 cardinal points, let us located here. Okay, and corresponding planes are like this. If I am going to consider first focal plane, which will be passed through the first focal point and it will be perpendicular to the principal axis. Likewise, second focal plane, this is your second focal plane, which will pass through the second focal point. Likewise, first and second principal planes passed through the first and second principal points and perpendicular to the principal axis. These two are the first and second nodal planes passed through first and second nodal points and perpendicular to the principal axis. Okay, so here if I am going to consider these planes in this figure, it will be complex to explain. Okay, so for simplicity I am going to remove all of these planes. Okay, but you just keep in your mind that planes are present at corresponding points. Here at F1 first focal plane, at F2 second focal plane, at P2 P1 and P2 first and second principal planes, N1 N2 at N1 N2 first and second nodal planes are present. Just keep in your mind. Now we are going to evaluate the location of cardinal points. Here in general, the matrix equation for output or image, whatever we discussed just in our previous slide, output information, that is your y o alpha o is equal to SM, system of matrix operated over initial information, that is your image information, which is in the input plane, which is in the input side, okay, which is in the input side, yi and alpha I. Here SM is called a system of matrix of optical system, which is a 2 cross 2 matrix. In general, it is represented as ABCD. Is any arbitrary 2 cross 2 matrix which is represents the general, which represents the general system of matrix. In general system of matrix, here ABCD, see, instead of SM we written ABCD. Here ABCD is any arbitrary 2 cross 2 matrix which represents in general system of matrix of that optical system. In general, I have to write over here, in general it will better, just wait. Here ABCD is any arbitrary 2 cross 2 matrix we consider here, which represents a general system of matrix of any optical system. So instead of SM, it is written as ABCD, a general system of matrix. Now we are going to write in equation format. If we are going to write this equation number 1 in equation format, see, equation number 1 written in the matrix format. So corresponding equation format means two equations we can found. YO will be equal to A into YI plus B into alpha I, that is your equation number 2. Then alpha O will be equal to C into YI plus D into alpha I, that is your equation number 3. Okay. Okay. Here again I written these two equations in this slide. Now we are going to evaluate first. We are going to evaluate first and location of first and second focal points, that is your F1 and F2. Okay, so here I am going to suggest one thing, that you just draw this figure in your note perfectly, and you have to draw this figure only in your exam perfectly. Okay, this figure is mark. That means if this question will be asked for 6 to 7 mark, if you drawn this figure perfectly, you can get 2 to 3 mark, 2 mark, minimum 2 mark itself. Okay, this figure itself 2 mark. So perfectly you just draw this figure in your note and practice it. To calculate the location of first focal point F1, consider ray 1, this one, incident ray 1. Consider incident ray 1. At the time of emergent, parallelly with principal axis, we can find angle alpha O equal to 0. Here this is the incident ray, enters into the optical system, which is enclosed by input and output plane, passed through this optical system. Obviously, if this is the focal point, obviously after passing through this optical system, the emergent ray will be parallel with principal axis. Okay, same thing I have been written. To calculate the location of first focal point, consider ray 1, this one, ray 1. Here this ray 1 starts from F1 and emerged this way, emerged from C along C dash. This is the emergent ray of ray 1. Here incidents on the input plane, passed through this optical system, which is enclosed in between input and output plane, and emerged at the point C parallelly with optical axis. Sorry, yes, optical axis or principal axis. Okay, if it is so, then alpha O here, if I am going to consider this angle, see, this angle is the angle of incidence or input angle. We can say the input angle of this object, which is at focal point, first focal point F1. So if this is your input angle alpha I, this is alpha I, then what will be the angle between this emergent ray and principal axis? Both are parallel with each other. If it is so, then the angle between emergent ray and principal axis is 0, because both are parallel with each other. Hence alpha O angle is equal to 0. Now the equation number 3 will be here equation number 3. This is your equation number 3, right? Here we have to substitute instead of alpha O equal to 0. That implies 0 equal to C into yi plus D into alpha I. So that implies yi by alpha I equal to minus D by C. Let this is your equation number 4. Now consider right angled triangle F1AL. Here this is your F1, this is your A, this is your L. F1AL, at point L this angle is your 90 degree, right? Tan alpha, if I'm going to consider tan alpha I, this angle is your alpha I, okay? Tan alpha I, then tan alpha I will be equal to this height and this length, or this is the base length, this is the height. So we can write AL by F1L. Here from the principal axis towards up, we are going to consider positive sign according to sign convention that we know. From input plane towards left, we have to consider negative, towards right we have to consider positive, and from the principal axis towards up positive, towards down it is negative. So here yi, as we are measuring from principal axis towards up, this yi will be positive according to sign convention. F1L length, this length we are considering from this point to this point, okay? As we are considering towards left from the input plane, then obviously it will be negative according to sign convention. So here this length from F1 to L, length is how much? X1, but we have to consider minus X1. Here minus X1. Got it? That implies X1 will be equal to minus yi by alpha I. By using equation number 4, here equation number 4 is your yi by alpha I. You just compare this equation and this equation, or just use this equation number 4. What we can get instead of yi by alpha I, what we can substitute? We can substitute minus d by c over here. Minus d by c, if I'm going to substitute instead of yi by alpha I, then we can found x1 equal to d by c. Let this is your equation number 5, and this equation number 5 represents the location of a first focal point from input plane towards left, okay, towards left. Here I written towards left in bracket. Why I written in the bracket? Here I am explaining carefully, you just watch. This is most important point. This x1, which is represented by equation number 5, depends on d and c values. So if it is so, this x1 value may be positive or may be negative. What I want to say, here we discussed in general way of an optical system, cardinal points of an optical system in general way. Practically, if we are going to consider this case, two thin lenses separated by a distance, combination of two thin lenses, what we are going to discuss in our next forthcoming class. For this case, this is the case that two thin lenses separated by a distance. For this case, we can found x1 value is positive. That means we have to consider, for this case we have to consider x1 towards right of the input plane, but in this figure particularly, f1, this f1 situated left to the input plane. So only for that we have here I written towards left, okay, only for that I written towards left. But if we consider any optical system, this x1 may be positive or may be negative. If positive will come, then we have to move towards right. If negative will come, then we have to move towards left. You can also observe in case of Ramsden eyepiece, what we are going to discuss in our forthcoming classes. Ramsden eyepiece, this x1 will become as negative value. But in case of hygiene eyepiece, this x1 value will become as positive. It is interesting. So here x1 depends upon D value and C value. This x1 may be positive, may be negative. But here I written in bracket towards left because in this particular figure f1 situated left to this input plane. But okay, you just keep these things in your mind, which is most important, right? Again, from a right angle triangle f1b p1, f1 f1 b p1, here this angle is your 90 degree. Now tan alpha I, this is your alpha I, tan alpha I, if I'm going to consider, then this height by this length. Okay, same thing it has been written, tan alpha I is equal to f1b, this one f1b, f1b, sorry, this is your p1b, instead of by mistake I written this is f1, but this is your p1b, this height p1b by f1 p1. Okay, f1 p1, here you can see p1b is nothing but this height, this height is your how much, yo. Okay, but for small angle, see, if tan alpha, first I have to correct it, just wait. This is your p1, right? p1 p1b by f1 p1. Okay, but for small angle, this tan alpha I is nothing but alpha I, and p1b from the figure, p1b, this height is nothing but is your yo, and as this height taken from the principal axis towards up, that will be the positive sign. Here f1 p1, this length taken from this point p1. So here from first principal plane, if we are going to move towards left according to sign convention, that will be the negative value we have to consider. Towards right, that will be the positive value. So here this distance f1 to p1, this distance is your f1. Okay, but as we are moving towards left according to sign convention, we are going to consider that will be the minus f1. Okay, this will be minus f1. So alpha I we found yo by minus f1, right? Same thing I have been written, alpha I equal to yo by minus f1. Let that is your equation number 4, sorry, equation number 6. Now we are going to put yo value from equation number 2 in equation number 6. Here this is your equation number 2, yo equal to ay plus b alpha I. Now we are going to substitute this yo value in equation number 6. Here ay plus b alpha I by f1. That implies f1 will be equal to minus a into yi plus b alpha I by alpha I. That implies f1 equal to minus a into yi by alpha I plus b. Let this is your equation number 7. Now put yi by alpha I value from equation number 4 in equation number 7. Here you can see this is your equation number 4. Equation number 4, in equation number 4, yi by alpha I is equal to minus d by c. Now we are going to substitute this value here. Instead of yi by alpha I, it is substituted by minus d by c plus b. So that implies f1 we found ad minus bc by c. Let this is your equation number 8. Now consider the determinant of the system of matrix of this dynamics. Here I marked as star this line. Try to understand carefully. Here, system of matrix of this dynamics. What is the dynamics? Here we considered this incident ray. This incident ray starts from F1, enters into the optical system through this input plane. At first principal plane, it is refracted and then moved parallel with the principal axis and emerged through output plane like this. So here we can get one translation. Here from F1 to B, one translation, then at B, one refraction, then it is moved without any deviation. So for this dynamics, or to represent this dynamics, we need two matrices. One is your translational matrix, another is your refraction matrix. May you remember in our last class we have been discussed this one. In system of matrix, what we have been discussed? We discussed that system of matrix act as operator. So here, if this is the output or is your image and this is your object, so here how many dynamics are there? One translation, here refraction 1, again translation, this is your one translation 1, translation 2, again here another refraction, again translation 3. So here we need 1, 2, 3, 4, 5 matrices. So if we know about object information, we are going to apply the system of matrix. That means multiplication of these 5 matrices, we can get the output. So how we are going to multiply? This is the initial, or this is the object, or in the input plane, it will multiply it first with T1, first translation matrix, then second, this is a first refraction matrix, then translational matrix 2, then refraction matrix 2, then translation matrix 3, like this. Okay. Likewise here, in this case, this is your refraction, this is your translation, and this is the output. Okay, this is the output. So two matrices required to represent this dynamics. So if this is your input or object information from where incident ray starts, this incident ray first translates from this point to this point, and at point B it is refracted. So what will be its system of matrix? Its system of matrix will be like this. This is your refraction, then translation or will be operated on object, then we can get the image information. Okay, same thing I have been written over here. Okay, consider the determinant of the system of matrix of this dynamics. Means here incident ray translated from F1 to B, one translation, and at B another one refraction. So what will the system of matrix? It will be R, which is a refraction matrix 2 cross 2, translation matrix again 2 cross 2, multiply. If both are multiplied with each other, then this system of matrix also 2 cross 2 matrix. Okay. So in general, we considered the system of matrix as A, B, C, D. And here this determinant value will be equal to mu I by mu O. Why it is and how it is, here carefully you just watch. Here for this dynamics, the system of matrix is one refraction matrix, one translational matrix. You just recall when we discussed the refraction matrix, that may be through convex surface, maybe it is mu1 greater than mu2, mu1 less than mu2, or concave. Through concave surface. These are the refraction matrices what we we evaluated at that time. You just find out its determinant. If I'm going to consider its determinant, what will the value is your mu1 by mu2. For this case also mu1 by mu2. For this case here 1 into mu1, this is 0, so obviously second part will be 0, so mu1 by mu2. So for each case, whatever the refraction matrix we are going to consider, its determinant will be mu1 by mu2. Okay, now consider translational matrix. In case of translational matrix, what will the determinant? Either you can consider in general format, or by considering mu is equal to 1, or for any for vacuum medium, what will be the determinant value? Here the determinant value is 1, here also 1, because this is 0, 1 into 1 minus this is 0, here determinant 1, this determinant value is 1. So here any translational matrix we are going to consider, the determinant value is your 1. Here in refraction case, the determinant value is your how much? Mu1 by mu2. Now if I'm going to consider the system of matrix, determinant of this system of matrix, which is multiplication of one refraction matrix and one translational matrix. Here any refraction matrix we are going to consider, its determinant is how much? Is your mu1 by mu2. And for translational matrix, the determinant is your 1. Already we discussed that here mu1 by mu2 can be written as mu I by mu O. Here I is your input, O is your output. So this mu1 by mu2 can be written as mu I by mu O into 1. So the value will be mu I by mu O. So this is one important information. Here I marked as star. Whatever I discussed in one line I represented and I discussed. Keep it in your mind. Okay, so here for this dynamics, the system of matrix is your Rm into one refraction and one translation. Translational matrix, multiplication of one refraction and one translational matrix. After multiplication we can get always mu I by mu O, and if I'm going to consider its determinant value, this will be AD minus BC. AD minus BC equal to mu I by mu O. Let this is your equation number 9. Now put this equation number 9 value in equation number 8. Here instead of AD minus BC, what we can put? We can put mu I by mu O. So that implies F1 we can found mu I by mu O into 1 by C. Let this is your equation number 10, and this equation number 10 represents the location of first focal point from first principal point towards left, or it is called its magnitude. Its magnitude is called the first focal length, or simply focal length. Okay, just wait, I have to correct it. Its magnitude is called as your first focal length. Just wait, I have to correct it first. Here this equation represents the location of first focal point, this one, from first principal point, from this one towards left, and this magnitude or this length is called as your first focal length. Okay, here I written first focal point from first principal point towards left in bracket. Why I written in bracket? See, for this particular figure in general, see here we are evaluating cardinal points and cardinal planes in general. Okay, in general. So particular for this figure, F1 situated left to this P1 point, first principal point. So only for that I written towards left in bracket. But actually for any arbitrary optical system which we are going to consider, then this F1 may be positive, may be negative, because this F1 depends upon this C value. See, mu I and mu O are the refractive indices, both are positive values, but C may be positive, may be negative. So f1 may be positive, may be negative. If positive value came for an arbitrary optical system, then we have to consider, then we have to take towards right of the principal point. If negative value will come, then we have to take towards left of this principal point P1. Okay, so you just keep these things in your mind. Now we are going to move our next slide. Here in this slide we are going to calculate second focal point f2. Okay, for that consider ray 2. This is your incident ray 2. At the time of parallel incidence with principal axis alpha I angle equal to 0. At the time of incidence, here as this ray 2 parallel with the principal axis, so obviously incident angle will be equal to 0 or alpha I angle. Here alpha I has definite angle, but here alpha I will be equal to 0 because incident ray and principal axis both are parallel with each other. So the equations 2 and 3 will be, here I am going to go to our previous slides. Here in equation number 2 and 3, if I am going to substitute alpha I equal to 0, then we can found yo equal to a yi, alpha o equal to c yi. Same thing I have been written over here. Yo equal to a into alpha I, alpha o equal to c into yi. Let this is your equation number 11 and this one is your equation number 12. Now dividing equation number 11 by 12, we get alpha o by yo equal to c by a. That implies alpha o equal to c by a into yo. Let this is your equation number 13. Now consider right angle triangle AMRF2. Where is your AMRF2? This is AMRF2. This is your 90-degree angle, right angle. For this triangle, if I am going to consider tan alpha O, that means this length MR by MF2. Okay, same thing it has been written, tan alpha O equal to MR by MF2. For small angle, tan alpha equal to alpha. Here tan alpha O equal to MR by MF2. Here MR taken as minus YO, this height. This height is your YO, but minus Y, because here we are considering the length below the principal axis. So according to sign convention, it will be negative. By MF2, MF2 means this distance is your plus x2. Why? Because we are considering the length right to the output plane. So according to sign convention, it will be considered as positive. Always we have to remember towards right of the output plane and principal plane, we are going to consider the positive. Towards left of the input and principal plane, considered as negative. Towards up from the principal axis, positive. Towards down, according to sign convention, the length will be negative. Just keep these things in your mind. Okay, so here alpha O we found minus yo by x2. Now just substitute alpha O value in equation number 13 here. That implies here alpha O substituted by this value, minus yo by x2 equal to c by a into yo. Yo got cancelled. We found x2 equal to minus a by c. Let this is your equation number 14. And this equation number 14 represents the location of second focal point here. See, this distance is your x2. Okay, this value minus a by o represents second focal point from the output plane towards right, from output plane towards right. Okay, here I written towards right because in this particular figure the location of second focal point, here the location of second focal point is right to this output plane. So I written towards right in this bracket, but actually this x2 value may be positive, may be negative. Okay, because this x2 value depends upon a value and c value. See here, do not bother about this negative value, do not bother about this negative value. This is in general expression. This x2 whatever represented in equation number 14, it is in general. Okay, so you should not bother about this negative value. But in this figure f2 situated right to the output plane, so I written towards right in bracket. But actually if we are going to consider any arbitrary optical system, then this x2 value may be positive, may be negative. At that time we have to consider, if positive value came, then we have to consider towards right from the output plane. If negative value came, then we have to consider towards left from this output plane. Okay, next we are going to move our next slide. Again consider the right angle triangle P2QF2. Here P2, Q and F2, this triangle. For this triangle, this is your 90 degree and this angle is your alpha O. Consider tan alpha O for this right angle triangle. We can found this height by this length. Okay, that is your P2Q by P2F2. But for the small angle, tan alpha O equal to P2Q by P2F2. Here P2Q will be considered as minus yi. See, this height is your yi. At the time of incidence, this is considered as minus yi, as it is taken from the principal axis towards down, so obviously it will be negative according to sign convention. So minus yi by P2F2. P2F2, this length is nothing but your focal length, this length taken as positive, F2 written here. Now put alpha O value in equation number 13. We get here in our previous slide, the equation number 13 is your this one, alpha O equal to C by A into YO. Instead of alpha O, we have to substitute this value, minus yi by F2. Minus yi by F2 is equal to C by A into YO. C by A into YO. That implies here, instead of YO substituted as Y, instead of YI, here it is substituted by YO by A by using equation number 11. Here in your equation number 11, what we have YO equal to A into YI. Same thing I have been written over here. So YI will be equal to YO by A. So instead of YI, written as YO by A by F2 is equal to C by A into YO. That implies here YO got cancelled, AA also got cancelled, and we found F2 equal to minus 1 by C. Let this is your equation number 15. So equation number 15 represents the location of second focal point from second principal point. So this is your second principal point. From second principal point towards right, we found the second focal point towards right, and its magnitude, if I'm going to consider its magnitude, is called as your second focal length or simply focal length. Okay, here I am going to repeat the same, that I written towards right in bracket. Why? Here in this figure you can see that F2 second focal point situated right to this second principal point. Only for that I written, because in this figure this F2 located right to this P2, but actually this F2 value, uh, as it is depends upon C, this F2 value uh, can be positive, can be negative for any arbitrary optical system. If we are going to consider any arbitrary optical system, this value may become as positive, may be negative. If a positive value will come, then we can say that we have to move towards right from this P2 principal point or second principal plane. If negative value will come, then we have to move towards left from this P2 second principal point or second principal plane. This is most important. You just keep these things in your mind. Okay. Now, the location of first and second focal planes are same with F1 and F2. Here we found first focal point. This is your second focal point. Focal planes passed through these points only. Already we have been discussed in our last class. This is the first focal plane, and plane will be passed through this second focal point, that is called as your second focal plane. And these two planes perpendicular should be perpendicular to the principal axis. So obviously the location of first and second focal planes are same with first and second focal points. Okay, now we are going to move our next slide to evaluate or to calculate the location of first and second principal points P1 and P2. Okay, so to calculate the location of first principal point P1, consider the length F1 P1 in figure. Here, this is your F1, this is your P1. Consider this length. F1 P1 is equal to sum of F1L, this length, this is L. Okay, F1L plus LP1. Okay, F1L plus LP1. That implies F1P1, F1P1. That means from this point to this point is nothing but your focal length. If I am going to consider this length from this first principal plane, so it will be considered as minus F1. So F1 P1 will be written as minus FP1, F1 minus F1 small f1 according to sign convention is equal to F1L, F1L length taken from input plane towards left side, this length. Okay, so this length will be considered as minus also, minus x1 according to sign convention. LP1, LP1 means L to P1, this length, how much? Plus R1, plus R1. Okay, so that implies R1 will be equal to x1 minus f1. That implies R1 equal to, instead of x1 it is written as d by c, instead of f1 it is written as mu I by mu o into 1 by c. Already we found these values in equation number 5 and 10. Just follow equation number 5. Here, this is your equation number 5. X1 we found d by c. In equation number 10, f1 is equal to mu I by mu o into 1 by c. Here the same we have been substituted instead of x1 and f1. After simplification, we found R1 equal to d minus mu I by mu o whole divided by c. Let this is your equation number 16. The equation number 16 represents the location of first principal point P1 from input plane. So here R1 is nothing but this distance from input plane towards right, towards right I not written, but from figure it can be perceived that it is from input towards right. How much distance we have to cover? R1 distance. Then we can found first principal point. But here you have to just remember that for any arbitrary optical system, this R1 value may be positive or may be negative, because this R1 value depends upon D and C values. So if we got positive value, then we have to move towards the right from the input plane. If we got negative value, then we have to move towards left from this input plane. Okay. Now we are going to evaluate second principal point, location of second principal point. To calculate the location of second principal point P2, consider the length P2 F2. From here, this is your P2, this is your F2 point. Consider this length. This length is the sum of MP2 here, MP2 this length plus MF2 this length. Okay. So that implies P2 F2 considered as plus small f2, because if we are going to consider the length from principal plane towards right, so obviously it will be considered as positive. Positive small f2, P2 F2 this length, P2 F2, okay, is equal to MP2. MP2 means MP2 this length from output plane towards left. This much length is nothing but your R2. As we are moving towards left, so according to sign convention, it will be considered as minus R2 plus MF2. MF2 means from M point to F2. That means we have to move right side. According to sign convention, this distance will be considered as positive, so plus x2. That implies R2 will be equal to x2 minus f2. Now we have to consider equation number 14 and 15. From equation number 14 and 15, we are going to substitute x2 value and f2 value. Here you can see in this is your 15 equation number 14 and 15. This is your 15 equation number 15. F2 we have to put instead of f2 minus 1 by c. In equation number 14, x2 instead of x2 we have to substitute minus a by c. So instead of x2 minus a by c, instead of f2 minus 1 by c. So x2 substituted by minus a by c, f2 substituted by minus 1 by c. Okay, that implies here this will be plus 1 by c minus a by c, 1 by c minus a by c. So obviously the numerator will be 1 minus a by c. Let this is your equation number 17 here. Okay, okay, let this is your equation number 17, and the equation number 17 mistakenly written 16. The equation number 17 represents the location of second principal point P2 from output plane. Okay, from output plane, this is the R2, this distance. From output plane we have to move towards left side. How much distance? This much distance, and we can found the location of second principal point. Here same thing I want to recall once again, that this R2 value may be positive, may be negative for any arbitrary optical system, because this R2 depends upon A and C values. If positive value we got, then we have to move towards right from the output plane. Here I not written, but if we got positive value, then we have to move towards right from this output plane. If we got negative value, then we have to move towards left of this output plane. Okay, this is most important point, you just remember. Location of here, as we know, the principal planes are passed through first and second principal points. So the location of a first and second principal planes are same with P1 and P2. So if we are going to consider the location of first principal plane, this plane will be passed through this point and perpendicular with the principal axis, and second principal plane will be passed through this second principal point and perpendicular with principal axis. So hence the location of first and second principal planes are same with the first and second principal points. That means at same with P1 and P2. Okay, now we are going to move to calculate the location of first and second nodal points N1 and N2 in our next slide. Okay, to calculate the location of first and second nodal points N1 and N2, we consider this figure. Okay, here location of principal point first and second focal points F1 and F2, we consider this figure, but to evaluate the location of first and second nodal points, the figure is somewhat different, this one. Okay, so here this is your input plane I1 I2, and this is your output plane O1 O2. In between input and output plane, a optical system is present. This is your P1 P2, that is your first principal and second principal points. This one first focal point, this is your second focal point of the optical system. Here I mark that with a star mark, first nodal point, this is your second nodal point. Some books drawn this figure as N1 nodal point 1 marked here, nodal point 2 marked here. Okay, so no issue about the marking of N1 and N2 in different books in different figures. Here let us N1 first nodal point is situated here and second nodal point is situated here. Okay, according to definition, if incident ray passed through first nodal point, then the emergent ray will be parallel with the incident ray, and the emergent ray seems to coming out from the second nodal point. This is the definition, and the nodal planes are passed through these two nodal points. So here this is the incident ray which is passed through the first nodal point, and the emergent ray seems to coming out from the another nodal point parallelly with incident ray. Okay, so from figure, alpha I, this I angle, this one alpha I, and alpha O, this angle, both are same because incident and emergent ray are parallel with each other. So alpha I and alpha O both are same. Let us alpha angle. Okay, because incident and emergent rays are parallel with each other. Then from equation number 2 and 3, I mistakenly written 2 and 3, what we have? We have this one and this one. If I'm going to go back, then I can find equation number 2 and 3. So these are equation number 2 and 3. Same equations written over here. Equation number 2 and 3. YO equal to A YI plus B alpha I. Alpha O equal to C YI plus D alpha I. Now the equations 2 and 3 will be, if I'm going to substitute instead of alpha I, alpha O equal to alpha, then these equations will be written as alpha O equal to A YI plus B. Instead of alpha I, we have to write alpha over here. Okay, alpha. Let this is your equation number 18. Then instead of alpha O, it is written as alpha equal to C YI plus D. Again, instead of alpha, it is written as alpha I, it is written as alpha. See, A and alpha seems to be equal. These two letters seems to be like. Only for that, I written A in red color. Okay, may it will be create confusion. So I written A in red color, alpha in black color. Okay, okay. So this is your equation number 18 and 19. For first nodal point, consider a right angled triangle ULN1. ULN1. Here, this is your right angle. Okay. If this angle is your alpha I, this angle will be how much? Will be 180 minus alpha I. See, whenever we consider the right angle triangle for any calculation, we consider the inside angle. Here, if I'm going to consider MRF2, here MRF2, I consider this triangle. This is your triangle. I consider the inside angle. Okay. Similarly, here F1AL triangle. F1AL triangle tan alpha I. This is also inside angle. Similarly, to calculate the nodal points, we have to consider the inside angle. But here alpha I is the outside angle, and this is the 90 degree. But we have to consider this angle. This angle is your 180 minus alpha I. So in right angle triangle ULN1 tan pi minus alpha I. This is your 180 or pi minus alpha I. Tan pi minus alpha I, which will be equal to minus, because tan pi minus theta is your minus tan theta. So it will be minus tan alpha I is equal to minus tan alpha, because alpha I considered as alpha, minus tan alpha equal to this length, the so-called height, this length, the so-called base, Lu by Ln1. But for small angle, tan alpha is your alpha, already minus is there, minus alpha equal to Lu. Here Lu considered as positive yi, because it is taken from principal axis towards up by z1, this one, this length. This is also considered as positive because this length taken from input plane towards right, so it is positive yi by z1. That implies yi here we found equal to minus alpha z1. Now put this yi value in equation number 19. Here in equation number 19, that means instead of yi we have to write what? Minus alpha z1. So that implies alpha, already alpha is equal to c into minus alpha z1 plus d alpha. That implies, just simplify here, alpha got cancelled. We found z1 equal to d minus 1 by c. Let this is your equation number 20. This z1 or equation number 20 represents the location of a first nodal point n1 from input plane. That means from input plane towards right. Okay. Now we are going to calculate the location of second nodal point. For location of second nodal point n2, consider right angle triangle VM n2. This is your V, this point is your V, M, this point M, this point n2. Okay. So here this is the outside angle. We have to consider this angle. This angle is nothing but pi minus alpha O. So for this triangle, tan pi minus alpha O equal to minus tan alpha O equal to minus tan, because alpha I equal to alpha O equal to alpha. So instead of alpha O, here it is written as alpha, minus tan alpha equal to this height. This is the height by this length base. This height is your MV by mn2, right? MV by mn2. But for small angle, this tan alpha will be alpha, already minus is there, so minus tan alpha will be equal to minus alpha for the small angle, equal to MV is considered as minus yo. Here this length taken from principal axis towards down, so this length is your minus yo according to sign convention, and from this output plane we consider this length. Okay, so this length considered from input output plane towards left, so obviously it will be considered as minus z2, right? So that implies yo equal to minus alpha z2. That implies z2 equal to minus yo by alpha. Let this is your equation number 21. Put yo value from 18, equation number 18, in 21. In 21, mistakenly written, this is your 21. First I have to correct it. Wait. 18. Put yo value from equation number 18 in 21. Where is your equation number 18? This one. In equation number 18, yo equal to a yi plus b alpha. Here it has been substituted. Instead of yo, it is substituted as a yi plus b alpha by alpha. Okay. Now put yi value from equation number 19 in above equation. Above equation means this one. From equation number 19. Where is your equation number 19? This one. This one is your equation number 19. So here alpha equal to c yi plus d alpha. So that implies here c yi is equal to alpha minus d alpha, right? That implies yi is equal to 1 minus d into alpha by c. Same thing, it has been written over here, 1 minus d by c into alpha. Okay, here 1 minus d by c into alpha. Okay, so instead of yi, here it is substituted this dot 1 minus d by c into alpha from equation number 19, plus b alpha written as such. Already a is there, a written here, 1 by alpha also written here. You just simplify here, alpha alpha got cancelled. We found z2 equal to minus a into 1 minus d by c plus b, right? That implies z2 equal to minus a into 1 minus d plus bc. You just add these two terms, we can get this one. That implies z2 equal to minus a, here minus a, this is minus ad, again minus plus ad, and this will be minus bc, ad minus bc by c. From equation number 9, we know this value ad minus bc is your mu I by mu o. Equation number 9. Here in equation number 9, we found mu I by mu o equal to ad minus bc. So instead of ad minus bc, we can substitute mu I by mu o. Here mu I by mu o minus a by c. Let this is your equation number 22, I think. Okay, this is your 22, equation number 22. Already 21 equation we have. Okay, this equation 22 represents the location of second nodal point N2 from output plane. From output plane towards this side, towards left. If we are going to move this much distance, then we can find second nodal point. Okay, here first I'm going to correct this equation number. This is your 22. So equation number 22 represents the location of second nodal point from output plane. Here I not written, you have to write by yourself. The nodal planes will be passed through corresponding nodal points. This is your first nodal plane and this is your second nodal plane, passed through corresponding nodal points. So obviously the location of nodal planes will same with nodal points N1 and N2. This sentence I not written here, you just write by yourself. Here we are going to consider some special cases. From previous results, what we found in equation number 5 and 14, if I'm going to consider equation number 5 and 14, we found x1 equal to d by c, x2 equal to minus a by c. You can search equation number 5 and 14. Here 14, x2 equal to minus a by c. Equation number 5 represents what? X1 equal to d by c. Here, okay. Then here equation number 5 and 14 represents what? Represents the location of first and second focal points from input and output planes. Then equation number 16 and 17, that is your R1 and R2. 16 and 17, equation number 16, this one, equation number 16, R1, this is your equation number 17. These equations, equation number 16 and 17, represents the location of first and second principal points from input and output planes. Or yes, input and output planes. Then equation number 20 and 22, these two equations represents the location of first and second nodal points from input and output planes. Okay. Then considering equation number 10 and 15, equation number 10 and 15, here 15 is your location of second focal point from second principal point, and equation number 10, if we are going to consider equation number 10, represents the location of first focal point from first principal point towards left, and for the second focal point, this is F2 is the location of second focal point from second principal point towards right. So equation number 10 and 15 represents the location of first and second focal points from first and second principal points and their magnitudes. If I'm going to consider magnitude, the magnitudes are called first and second focal lengths. Here these values x1, x2, r1, r2, z1, z2, f1, f2 are depends upon here a d c. Here x1 depends upon dc, x2 depends upon ac, here dc, ac, dc, ac, cc. So these values depends upon a d c. So these values, if I'm going to consider x1 or x2 or r1, r2, these values may be positive, maybe we can get positive or negative for an any arbitrary optical system. So if we get positive, then we have to move towards right. If we get negative, we have to move towards left. Most important, just remember this one. Okay, now the special case here we consider, if mu I equal to mu o. When mu I equal to mu o, that means input side refractive index, this is your mu I refractive index, input side refractive index, and output side refractive index. If both are same, then the results what we can get here. Here r1 will be equal to d minus 1 by c, z1 equal to d minus 1 by c, r1 equal to z1. Similarly, r2 is your 1 minus a by c, z2, if mu1 equal to mu2, then this will be 1 minus a by c. That means r2 equal to z2, r2 equal to z2. That means this represents the location of first and second principal and nodal points are coincided with each other. If mu I equal to mu o, input side and output side refractive index if same, then this nodal points n1 and n2 will coincide on principal points p1, p2. When mu I equal to mu o, we get what we can get, f1 is your what, mu I by mu o into 1 by c, here minus 1 by c, this will be 1. So f1 we can found f1 equal to minus f2, f1 equal to minus f2, or we can say f1 magnitude equal to f2 magnitude. That means left side focal length is equal to right side focal length if input and output refractive indices are same. Here this represents the magnitude of first and second focal length are same, what I discussed. Now this is most important. Consider r1 minus r2, okay, and z1 minus z2. First consider r1 minus r2. r1 minus r2 means here r1 value is your what, d minus mu I by mu o by c minus 1 minus a by c. You just calculate difference between r1 minus r2. We can found this value, d minus mu I by mu o minus 1 plus a by c, z minus z2. So z1 minus z2, z1 is your d minus 1 by c, z2 is your mu I by mu o minus a by c. If I subtract these two values, we found d minus mu I by mu o minus 1 plus a by c, both are same. From above two equations, these two equations tells that what, from above two equations what we found, r1 minus r2, this value is equal to z1 minus z2. That means this is your r1, okay, and this is your r2. If I'm going to subtract these two lengths, it will be equal to subtraction of these two lengths. This one is your z1, right, this one is your z2, this one here, see, this one is your z1, and this is from here, this from output plane, okay. So this is your z2, okay, z1 minus z2 will be equal to r1 minus r2. Here I written. This represents what? This represents the separation of principal points and nodal points are same, which is not depends upon mu I and mu O. Okay, so may it will coincide or not coincide, it is not matter, but this separation between principal point and separation between nodal points will be same. This is most important point that you have to remember. This is one of the important short question. Short question will ask that, is it true or not? Yes, it is true. It is not a depend. It's not depend upon mu I and mu O. Okay. I suggest you just remember this one, this equation, and this equation. This one. These two results are very much important. And also I suggest you have to remember these equations. Equation number 5, 4, that is your represents of location of focal points, principal points, and nodal points. So here we discussed in this class. The video is somewhat long, so you with patience you have to watch this video and note. You have to do your note for your exam. In this video we discussed location of cardinal points and planes of an optical system in general. Up to this much we have been completed. Then next topic is your idea of dispersion. This topic we are going to discuss later. But next class we are going to discuss application to thick lens and thin lens. What we discussed. We discussed matrix formulation of geometrical optics, cardinal location of cardinal points. So we have to apply those things whatever we have been studied. So application of matrix formulation, that is your to calculate the system of matrix for thick lens and thin lens, and also cardinal points. We have to evaluate the cardinal points of thick lens and thin lens in our next class. Okay, thank you so much for watching this video. Thank you.